should we get sharps out here? The contradictions, redundant preachings. Think you can tame me?
Hello. Today we're going to look at the semi-empirical mass formula, or I could have called this the binding energy of the nucleus.
There's a
or
lot
I
of
could have called
material
it
in here.
what holds the nucleus together, or I could have called it why can't you have
Nope,
any
E2.
number of protons
I'll just be
and
E2.
neutrons
That's fine.
in a nucleus. So this is a subject based on nuclear physics, and if you haven't already done so, I advise you to watch my videos
this guy, he did
in
good.
the
This
A-level
is
playlist
clean
on the nuclear
stuff, but
radius,
he's obviously
nuclear
Indian,
physics,
so
and
you
nuclear fission
gotta
and
adjust.
fusion, because that will give a background to what we're now going to cover. This material is more than A-level. This is essentially university level physics. We know that an atom consists of a central nucleus, which is positively charged, with, and I'm talking classically here, orbiting
Motivated.
electrons. We know that the nucleus itself consists of protons.
Well, I wanted to do this specifically
and
for
neutrons.
this, right?
Protons are positively charged, so they
one more.
contribute to
There
the
we go.
positive charge of the nucleus. Neutrons have no charge at all and don't contribute to the charge, but the net charge on the
Exclusive
nucleus
and
is positive. And there are an equal number
mutual
of positive
and-
charges, that is protons in the
Well,
nucleus,
we getting into
as
that.
there are negative charges, electrons, orbiting the nucleus.
Well,
Now,
I
as
just
we
want to keep
saw
this
at
one out
A-level,
because it's
if you
funsies
make
for
a
me.
plot of the number of neutrons versus the number of protons, the number of neutrons we put as n, the number of protons we use z. If you make a plot, this, I'm firstly just going to draw a line. That line is n equals z. That would be the number of neutrons equals the number of protons. But if you look at all the stable nuclei that there are, what you find is that at the low end, n does indeed equal z. But then the line diverts off toward the neutron end. And you find that stable nuclei with high values of z have more neutrons than they have protons. So there is an excess of neutrons in stable nuclei at the high end.
Okay,
In other words,
so
when Z gets larger,
once I have that
the
whole
number of
observation,
neutrons exceeds
it
the number of
is
protons.
in fuzz.
You also find
So,
that there
like,
are
remember I was like, that's
unstable
super clean?
nuclei
Well, the
surrounding
scowl
this line, and
wouldn't
I'll
be
talk about
compressed
what I mean by
correctly.
unstable in just a moment.
It makes
so
it a little bit more stable, but it's got some fuzz, right?
Both
Right?
above
They're
and
not, but I want to
below
cover them
this
up.
line.
They're
So stable nuclei represented by the crosses,
There's
unstable
in a stone
nuclei are represented by the circles, and if you like, we could draw a dotted line around all of this. This is nothing more than
this
a
is your
container.
cosmic radiation background.
And that dotted line shows you all the nuclei that you can find naturally occurring. You don't find any here. You don't find any here.
If
you
I
don't
track
find
this
any
line like it's my
above
X and Y,
this point
this
here.
time in the morning
And
to
what we're
this
going to ask
time
in
here,
this
I can
video
track
is
this unit like
why?
it's a square.
Well, let's first
see if I
consider
can find
what
a better
happens
one
with
here.
these unstable nuclei. Now, as I've said, in
That'll
the
do, but I don't know
series
what
of
this for.
circles which are above
it's
the
in here
stable
about.
line, basically you've got excess
Where is it?
neutrons.
Something
And
real.
below the stable line, you've essentially got
You got a
excess
field.
protons. And what happens
Okay,
with
get
those
out here.
unstable nuclei is that they will decay, they will change in order to get onto the stable line. So if you've got an excess of neutrons, what that means is that a neutron is going to decay into a proton. So you get a neutron becomes a proton plus an electron plus an anti-electron neutrino. If, on the other hand, you've got an excess of protons,
We can't do that. In fact,
then a proton
I'm moving fast.
will
Just
convert
let it
into a
happen.
neutron.
You'll understand it later when you have
So
when you
proton
have yours done,
converts into a neutron
right?
plus a
Right? Because you
positron
probably have a hard
plus
time.
an electron neutrino. We've seen those formulae before at A level. And what is actually happening is that if you're here at this unstable nucleus here, what you're going to do is you've got too many
depending
neutrons.
where you are living.
So if you convert a neutron to a proton, the neutron number will fall by 1, but the proton number will increase by 1. So what you'll essentially do, let me just draw it here. If that's your unstable position, that's this one here, you will fall down 1 on the neutron scale, but you'll increase 1 on the proton scale, so effectively you'll fall down in that direction onto a stable nucleus. So you'll become stable by decreasing the number of
I'll notice that, and I'll be like,
neutrons by 1, but increasing the number of protons by 1. Similarly, if you're on this position here where you're proton rich and you're going to change protons to neutrons, what you're going to do then, if you are at this position here, let's say, is you're going to decrease the number of protons by 1 and increase the number of neutrons by 1. So essentially, your pattern, let's move this up a little bit like this, your pattern will be to decrease the number of protons by 1, increase the number of neutrons by 1, so you're moving diagonally in this direction onto the line of stability.
But
so in both cases,
there she is.
You are changing either a neutron to a proton or a proton to a neutron, and what you do
if
is
you
you'll
do
notice
them differently,
you emit either electrons or positrons. Now, before anybody knew what electrons were, this emission was given a name. It was called beta.
Yeah.
In fact, people who were studying nuclei and their decay found that there were 3 types of emissions: alpha, beta, and gamma. Alpha was positively charged, beta was negatively charged,
vector,
and gamma wasn't charged
so it's
at
an
all.
X with an arrow over it. Then we got
and these
gradient and
emissions
delta.
are called beta
what is
decays.
this? I forget. Triple
beta
integral closed volume, and I have K-I-N-G,
So
right?
this decay
Closed
happens
surface
by
bar,
what's called beta decay, which is simply
closed
if you're
cylinder,
changing a neutron to a
M-A-R-K.
proton, you emit
Mark it.
an
I want you to
electron.
get there. Take
If you're
trip.
changing a proton to a neutron, you emit a positron. And this is the way that unstable nuclei get back onto the stable line. If you get to the very high end, you don't get electron emission anymore, you get alpha particle emission. Suddenly you've got to start reducing by significant numbers of neutrons and
these
protons.
2 lines right here are 6373 megaparsecs away from me in Faro. Not wrong, we'll be doing the same geometry.
Will reduce its neutron number by 2 and its proton
like
number by 2
Warhammer,
and move
how
on
you
to
play the game.
a stable position in that way.
Starts to be U units. I can run a single line. I can expect some people, if I had do this and go in there, then the job, the Hadron Collider.
What is causing this? And if we are speculating that there is a nuclear force, and we are, so we'll say here is the nucleus.
Means I had to know before I put it in there, because without it being here, it's going to drag, and it's going to be its own one particle that Heisenberg unsure of T's and N's and how people are getting together, optics, windage.
Which will be a repulsive force.
The
so
photo
was
in a gradient form, or delta.
If the nucleus is
I could say that a delta is, near the gradient, let's say. Where is it? Well, at any rate, gradient times,
and that force must be stronger than the Coulomb force that is trying to push it apart.
I'm not sure
if
at the
there
moment.
is this nuclear force,
Derivative,
which is essentially putting its
Delta,
arms around the
times
nucleus and saying, I'm
derivative
going to hold you together,
is an unsure principle on N's and P's and golden ratios of in the delta position where they make it work. It's emitting beta radiation of what the correct shadow problem look like, because you'll get E1, E2 symmetry, E, but not E2, right, on a combinational frequency permutation.
Well, if you were,
that's heavy stuff.
Thought experiment. If you were to take a set of scales,
money is based on the coin press in Caligula's model, because it's real hard to do plus T, depending on which. It's
so we've got Z
trip down the rabbit hole.
and N neutrons, but you just take the number of protons and the number of neutrons.
Talk about a hot line, a low line, a cold line. I'll show it to you here, and we'll bring it
and put them on these scales. And on the other scale, you put the actual nucleus itself,
or here,
which contains Z protons and N neutrons.
Sure, definitely put anything on the extruder here.
That the mass of the individual protons and neutrons,
you have to know from here that you're putting these in here, or be able to finish off with a scale that's appropriate.
There is what is called a mass deficit. Some of this mass has been lost.
But the first one, is banged right next to each other. The quest is you were supposed to do it now.
And how does mass get converted?
Now you remember generally what it looked like,
energy?
Right? Kinda.
Well,
Kinda. How'd you get there? How'd you get there?
So what we're saying is that this very tiny amount of mass that is the deficit between the individual constituent particles.
This is his stuff. I just condensed it like this pen's roll. So I can do it in there's Z time. What is this? It's a rational, or it's a complex conjugative, right? Z with a with a point, could be a P number, could be an
10 to the minus 27 kilograms.
But that was my note. They did not start that way. But I was like, oh, well, that's kind of a cool way to. I got 3 of them. Alright, and then okay, so then they're doing all this, and you can take a space-time video from YouTube and turn it into this, you say, huh?
C squared is 9 times 10
very
to the 16.
interesting.
So you're already, that's almost 10 to the 17th, you're already converting that, and that will be in joules. And if you want to convert joules to electron volts,
Milgram experiment.
Not quite this, but you multiply by 10 to the 19. You actually divide by 1.6 times 10 to the minus 19, but we'll just look at orders of magnitude.
Negative reinforcement training.
So you can see that this is essentially 10 to the 17, this is 10 to the 19. All of this combined is a massive 10 to the 36 to get an energy in 10 to the 36 to get an energy in electron volts. So even though you've got a very, very small mass, smaller than the mass of a proton,
this here, I could have gone targets, right? But I go coals because it's good real estate, and they're good with like whatever they real estate into their cubic bricks on the mods and the periods of the. Where my skid steer guy go again?
Well, how are we going to measure this binding energy? Well, on the face of it, it's pretty straightforward, because we know that we've just got to find the mass deficit and multiply it by C squared. Well, to find the mass deficit, what we need to do is to multiply the mass of a proton by the number of protons, plus the mass of a neutron, which we know, times the number of neutrons, and subtract from it the nuclear mass of the atom. Trouble is, measuring
just in this electron position now. And remember, I'm like forbidden S order and P order.
Atomic masses is very easy. John Dalton, for example, the chemist, was measuring atomic masses way back in 1803.
A bunch of different fun ways
long
to do it.
before, 100 years before anybody even knew what a nucleus consisted of. John Dalton was measuring atomic masses.
Moving Stonehenge into the sprinkle factory, turn it into Mallows to keep the light bill going, to be me.
From atomic masses and the knowledge of the mass of a proton and the mass of a neutron, which we can measure. So let's consider an atom, which I will give the symbol X. It doesn't stand for anything, it's just any atom which has Z protons and A nucleons.
This would look familiar to him.
Protons plus neutrons. So essentially A is equal to protons plus neutrons. So if you want to know how many neutrons
I don't know if I got it all the way good, but I know I'd be good.
Neutrons. So what is going to be the constituent bits of this atom? Well, there are going to be Z protons, so we multiply
this is quark in general because the main line's not some crazy hot mess garbage of this step gauge away from you talking about how comfortable you feel about this
then, of course, there'll be
conversation.
Electrons, and there are always the same number of electrons as there are protons, so there'll be Z electrons. So we multiply the mass of the electron by Z, and that gives us the total mass. And to convert that to energy, we have to multiply by C squared. So all of that is a mass multiplied by C squared gives you an energy. And that is going to be equal to the atomic mass,
just
so I'll put M at, atomic mass, of this element here,
right here.
X, Z, A, plus the binding energy of the nucleus, plus, if I can get it in, the binding energy of the atom. Because remember, not only is the
9.8
nucleus
meters per
bound,
second squared.
but the atom
FMA
is bound.
squared.
A hydrogen atom, for example,
Sometimes, not all the time.
binding energy of a hydrogen atom at its lowest level is minus 13.6 electron volts. In other words,
Ricci
you have
tensor
to
Hangman
provide,
right here.
you've got an electron, if you've got a hydrogen atom, the electron is bound to that atom.
Well, it's physics
And if you
hangman,
want
it's
to
Ricci's
get that
tensor.
atom to escape, you have to provide it with more than 13.6 electron volts in order to give it enough energy to escape. This is, of course, nothing more than the
So
photoelectric
hopefully
effect.
we
Here is the
conducted that
hydrogen
experiment
atom. It's
here,
got
and
one
it'll be
proton,
good with
it's
whatever
got one
marine I'm
orbiting
running down for
electron.
him.
The positive and the minus charges are
Yep, Vero, I got this.
attracting, and that means that the electron is bound to the atom, and it is
In this
bound
area
by
right here.
13.6 electron volts. You have to provide that to get it out. The photoelectric effect
Okay, thank
doesn't
you
use
very much,
hydrogen,
A-level
it uses
physics.
a metal.
This was
And what it
a
says
good
is
use
if you
of time.
shine light
Carl Sagan would be proud.